All right, now we're going to move on to section 3.7, talking about vectors, and then right after that, section 3.8, which is methods for adding vectors together. So we're starting off on page 45 in your text. All right, so first off, let's contrast several different kinds of quantities. So we can categorize quantities in several different ways. Scalar quantities, and then also quantities called vectors. Scalar quantities are the type of quantities we normally deal with. So a scalar quantity is a magnitude with a number and a unit. So typical examples of a scalar quantity would be like 4 gallons, 12 feet, 3 inches, a number and a unit. So that's very common. Then we have vector quantities. Vector quantities differ in that vector quantities not only include a number and a unit, but also a direction. So what would be some examples of vectors? A common everyday example would be, let's say you're listening to the radio or watching TV and there's a weather report and the meteorologist says that the wind is 20 miles per hour out of the northwest. So the meteorologist is reporting a number, 20, units, miles per hour, and a direction out of the northeast. Another one would be, let's say, in the civil engineering field. It's quite common to see, for instance, a site plan for a property, and if you have a property where a boundary is a straight line, they're not all straight lines, but if you have a boundary that's a straight line, it'll typically be marked not only with the length of that boundary line, but also the direction as well. And you'll have a little arrow pointing in the direction, but also you'll be given the bearing that shows the direction. Typically, it would be the direction in which the surveyors would have surveyed the boundary. And another one is forces in engineering problems are vectors as well, and we'll deal with some of those in some of our upcoming chapters. So as a quick example of that, let's say you have, here's a simple kind of example that we'll cover. Let's say you have some weight, and let's say that weight is being supported by some cables like that. So the forces in those cables can all be shown as vectors. You have the cable that's directly supporting the weight has a force in it pulling down. Then you have this cable connected to this wall is pulling out this way, and then the force in that cable is pulling up that way. So you could show those three forces as vectors, meaning there's some kind of a force in terms of pounds or newtons, and then there's also a direction. Okay, now in our study of vectors, we're going to use a coordinate system for measuring angles. So here's, in this textbook, here's the coordinate system that will be used. So 0 degrees will be in the direction that we normally think of as east, 90 degrees in the north direction, 180 degrees west, 270 degrees in what we would think of as the south direction. So 0 is to the east, and the angles increase counterclockwise. So that's the one that we'll use in these kinds of vector problems. Okay, so that's really just a description of what vectors are, and so we've pretty much covered most of section 3.7. But let me just briefly mention this. Take a look at the example at the top of page 46. Here's a real simple example. It's showing that somebody is driving from Atlanta to Washington. But first off, they're going via St. Louis. So you go from Atlanta, you're driving northwest to St. Louis, and then you're driving from St. Louis to Washington. And those drives can be shown as vectors. So you have, I'll just mark it A for Atlanta, then you're driving up this way to St. Louis, and then driving over to Washington. So that'll be shown something like this. Okay. So what we're going to be getting into then in this next section 3.8 is looking at how you would then add those together and get a result. Just like when we add together 2 plus 2 and get 4, what do you get when you add vectors together? So in this case, if you add vectors together, the way we define the answer is we define it as a resultant. And the resultant can be seen if you draw a line from the starting point to the ending point. In other words, what we're imagining is the result of driving from Atlanta to St. Louis and to St. Louis is Washington is that you're in Washington. So it would be equivalent to if you just drove directly from Atlanta to Washington. So this is what we would call the resultant. And the resultant can then be defined as a vector quantity in terms of number, unit, and direction. So what you would do to define the resultant is you would measure it for its length, and then you would use a protractor and measure the angle. And you'd be imagining the coordinate system is like this: 0 degrees, 90 degrees, and then you would be measuring that angle. And you can see the example in the textbook shows that it's an angle of 51 degrees. So anyway, that's just a quick introduction to what's going to happen in the next section. The methods for adding vectors end up with what we call a resultant, which is the addition of the vectors. All right, and we're going to illustrate this by taking a look at example 3.3 and 3.4. Now before we do that, there are two different methods that are discussed here. You can see in the introductory paragraph for section 3.8, there are two methods. So section 3.8, we have the polygon method and the parallelogram method. So here's just a brief discussion about what they mean. So let's say, for instance, well, the previous example I talked about of driving from Atlanta to St. Louis and Washington, that is the polygon method. So let's say you have a number of vectors you're adding together. Let's say you have this vector, and this vector, and this vector, and this vector. You got 4 of them strung together, and then your resultant would be from your starting point to your ending point. I'll just abbreviate it R for resultant. So this is the polygon method, where you're just stringing the vectors along from head to tail of the arrows. And then you just draw from the starting point to the ending point. The polygon method is fairly restrictive. The polygon method is only used if you only have two vectors you're adding together. Then you can use the parallelogram method. So this one goes something like this. Let's say you have two vectors. One vector is like this, and the other vector, say, is like that, and you want to add them together. It's called a parallelogram method because essentially what you're doing is you imagine these two vectors as the sides of a parallelogram, and what you're doing is you're kind of completing it and imagining that it is a closed figure. So in other words, this dotted line is just a copy of this vector, and then this dotted line over here is a copy of that vector. So you're completing a four-sided figure. And then your resultant is from your starting point to the opposite corner of the parallelogram that you sketched. That would be your resultant. You could also use the polygon method here. You could, instead of doing the parallelogram method, you could merely copy this vector and stick it on the end of this vector, and your resultant would be the very same thing. Or you could take this vector and copy it and stick it on the end of this vector, and you'd end up in the same place. So you could apply the polygon method in several different ways, or you could use the parallelogram method. Either one would give you the same result. All right, so let's illustrate this by going through example 3.3 at the bottom of page 47. Now these methods are graphical methods, so you're going to be sketching on graph paper. So what I'd like you to do then is to open up your workbook, and there is a section on vectors in your workbook starting on page 22. So this is example 3.3, page 47 in the textbook, but you're going to be doing your work here on page 22 in the workbook. So here's a piece of graph paper where you can follow along. Hopefully you can see this okay. Okay, so in these graphical methods, in any kind of graphing that you do, there's a couple of key things you want to put in here. One is you want to have a title for any kind of graph that you do. It's already on here, example 3.3. In this case, since we're working with vectors, you want to indicate direction. In this case, for this particular problem, we're showing a north arrow and we're showing a scale. So in this problem, this is a problem where a ship is at sea. On the first day it goes 100 kilometers north, and on the second day 60 kilometers northeast, and then 120 kilometers due east on the third day. Find the resultant displacement. So we're going to use the polygon method, and we're just going to string those three vectors together. All right, so in setting these up, I've set up the coordinate system and the scale for you. In some of the upcoming ones, you can do that yourself. I set the coordinate system up here because or going north, northeast, and then east, if I had set the coordinate system up in the middle of the page, we'd probably run off the page. So this is just to give more room here. So we'll just start with, oh, and the other thing I want to add in too is you want to make sure that anything you do is dated. So I'm doing this on the 21st, so I'm going to put a date up here and make sure no matter what you're doing, writing, graphical work, or anything, you always want to put a date on there. All right, so the first vector is 100 kilometers due north. Now I've got a scale of a half inch equals 20 kilometers. So I do have to do a little calculation. So the first, and I can do it right here on the graph, so 100 kilometers, and I'm going to apply the scale of a half inch for every 20 kilometers, because I need to know how long to draw this line on the graph. So 100 divided by 20 is 5, 5 times a half is 2.5. So this is going to be, so this is a conversion. So I know the 100 kilometer line on this graph is 2.5 inches long. And I know it's due north. Now another thing I want to say is it might be handy if you have, well, you're going to need a protractor. And if your protractor has, some protractors actually have a measuring scale along the bottom. This one has inches along the bottom. So I can use it for not only marking out the straight line vector, but then at the end measuring angles. If your protractor doesn't have a scale on the bottom, then you'll need some other kind of measuring scale. And also, in the back of the room, on top of the cabinets, there's a container marked measurement for physics. So if you need to pull out one of these scales for the purpose of this exercise, you can do that. All right, so now I know 2.5 inches for the first vector due north. So let me mark that out. So you can be following along here. So 2.5 inches will be like right up here. So there's the first vector right there. Goes from the origin of the axis up to that point. And then we have the next one on the second day, 60 kilometers. So again, I have to apply the scale, 60 kilometers times a half inch for every 20 kilometers, and then multiply it by a half inch. So this is 1.5 inches long. Now this one is northeast, which will be off at implying a 45-degree angle. So the first thing I would need to do is use my protractor and mark off, make sure I know what that direction is. Mark this off at a 45-degree angle. It'll be up in that direction. And then I want to make it 1.5 inches long, so then we can mark off 1.5 inches, and it'll be right in there. All right, so I drew it a little bit too long just to get the direction, and then so it comes right up to here. And then on the third day, 120 kilometers due east. So again, apply the scale, 120 kilometers times half inch for every 20 kilometers, and that will be 3 inches long. So now I'm going to go due east 3 inches from that point. So we have the 3 vectors drawn head to tail. And And then your resultant is going to be from the starting point, which was right down here, to the ending point. So you could draw that line as the resultant, which is the addition of the three vectors. All right, now, and I'll just mark it R for resultant. Then the question is, what is the resultant? So now you just have to work backwards. First, what we'll do is we'll measure the length of the resultant with our scale, and we've got that. I've got that at about 5.5 inches. So I can just do my work right here on the graph. So the resultant is 5.5 inches long, but I want it in kilometers. So we have to now go back and use the scale, which is 20 kilometers for every half inch, and that ends up being 220. 5.5 times 20, and then divided by a half. So that ends up being 220 kilometers. Now that's not a sufficient answer. I also need direction, because this is the resultant is a vector, so it has direction. So I'm going to now measure. I'm going to measure this angle from 0, because remember we're measuring from east at 0 counterclockwise. So I can stick the protractor on there, and that measures out. I've got about 41 degrees. So the resultant is 220 kilometers at 41 degrees, which is the sum total of having gone that direction, that direction, that direction. So there's that example. The answers don't exactly match what's in the book, but pretty close. And there's a pretty good illustration of how to do it there on the top of page 48. Okay, so here's what I want to leave you with then. There is the parallelogram example is example 3.4. You can see the illustration of that. It's pretty simplistic. It's just two vectors involved there. And so what I'd like you to do for an assignment is now to do problems 13 and 15. So if you look on the, let me write this up here. And this is on your schedule sheet that you have. So your homework would be problems 3.13 and 3.15. Now these are problems that are at the end of the chapter, and those are on the bottom of page 63 and the top of page 64. And to work these, you also have worksheets in the workbook. So you'll notice on page 24 and 25 in the workbook, I left you with some graph paper. But you are going to have to declare your scale and draw your coordinates in an appropriate place so that everything fits on the graph paper. And also, don't pick a scale that's so small that you can hardly see what you're doing, and obviously you don't pick a scale so that the vectors kind of run off the paper. So you'll have to work on that one a little bit. All right, so that's your homework, and then we'll continue on this tomorrow. Well, actually, tomorrow I think you'll probably have your tests on chapters 2 through 4, and then I'll see you Wednesday. All right, I heard the laughing. I'm getting confused on my courses. Okay, your chapter 2 through 4 test is in geometry and trigonometry, so forget I said that, and I'll see you when I get back.